Good morning. In today's lecture, I will go through design of sequential circuits. But before starting the design, let's finish last example. Last example, we already done this and finished it here. But I said, how about if we need to make this in a flip-flop instead of using if we need to get the equations using the state table or using the kernel maps instead of using the equations shown here. So just basically, I would like to make another approach, which is using the states using the kernel maps. So before starting the analysis, let's look. I'm going to erase this. Look at the state table, and we need to determine the minterms for each one. So our target is to look at next state's output. So we have 3 kernel maps for each one. Then look at the order y1, y2, x. So by making a value for each one, m0, m1, m2, and so on, so we will assign, or by looking at the state table, look at state table. Then we can say, let's look at y1 star, or the next state, y1 star. What are the minterms associated with it? So we will see for y1 star, here 1, here is 1, here is 1, which is 3, 5, 7. So the minterms are 3, 5, 7. Then for y2 star, the minterms are y2 star we have at 1, 5, 7. 1, 5, 7. Then for z, the minterms are at 6, 7. Then we can do the k-maps, as we can do easy, which is we have or we can connect this to k-maps, so such that 3, 5, 7. But we will keep in mind, when we draw the k-maps, it will be different than what we used to deal with in the past. In the past, we used to make k-maps like this. We used to say, for example, our variables are y1, y2, x. That was our variable. So we used to say, here is x, here is y1, y2. That was in the past. So we used to say here is m0, 1, 2, 3, 4, here's 4, 5, 6, 7, right? That was used in the past in the regular k-maps. But here in our design, we will try to flip it. Flip it like what? We will try to make it like this. So here will be y1, y2, and here is x. So it will be like 0, 1, 2, 3, 4, 5, 6, 7. So it's the same way, but just make it shift 90 degrees and then do a mirror. First shift 90 degrees and a mirror. Okay? So you see y1, y2, and x here. Clear? So we will use this in chapter 5 problems, which is whenever we are in design or when we need to use kernel maps, only for this part. Otherwise, you can use your own kernel maps. Okay, what's the point of using this? If you said, like, I prefer to use the old one, that's fine, you can use it. But why we didn't create this or the other version of kernel maps? We did this if you are drawing the state table into the Mealy model or Moore model, then the best way is to use this one. While if you make the generalized state table, you can use the old one, that's fine. But I don't want you to be confused. Should I use this one or the other one? Either ways, or what I prefer in chapter 9 of chapter 5, this one, we will use this version of kernel maps. Okay, what's the point? Let's redraw this table, state table, into, since this problem in Moore model, let's make it in Moore model. Moore model, basically we have present states, inputs, outputs. The output is not with the states. So that's what's Moore's model. So basically, here we have a sign of values of the states. So we have 0, 0, 0, 1, 1, 0, 1, 1. Then here are the inputs. So after assigning the values, we can replace this version like this. So presents, states, y1, y2. Here is inputs, x, 0, 1. Here is outputs. So instead of making the variables a and b, we will assign values 0, 0, 0, 0, 1, 1, 0, 1, 1. So here is 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1. Then, after that, what's the nice feature of it? The nice parts, when you look at this parts, or actually, this should be y1, y2, star. So look at those that I count them in red. This will be associated with y1. So y1 star, I will just copy them from the table, from the sequence. So here is 0, 0, 0, 1, 0, 1, 1, here is 0, like this. Then locates for y2. Let me choose different color like blue. So I'm going to copy them here as y2 star. So it will be 0, 1, 0, 0, 0, 1, 0, 1. Okay? Then, regarding to the outputs here, it can be for both columns. So 0, 0, 0, 1, 0, 0, 0, 1. That's why we prefer to use this kernel map, so you can copy this from the original Moore model, or it can be applied for Mealy model the same way. Okay? So this is here for Z. Then let's just make sure, is this consistent if what's the midterms that we got here? Let's see. Most likely, again, the terms here, like this is 0, 1, 2, 3, 4, 5. I'm sorry, here 4, 5, 6, 7. So here we have M3. I think, do we have the right sequence? Okay, M3, M5, M7. Here is M1, M5, M7. Here is I think for Z I mix it up. I think for Z there should be, let's keep Z later, but I'm just looking at Y1, Y2 star. So let's compare this, what we have here, 3, 5, 7, 1, 5, 7. Here we have 3, 5, 7, 1, 5, 7. You see? So, which is basically the same way. Then instead of finding the midterms, this is another way of doing it. Then for Z, how we can put this, which is most likely it should be associated with the it should be associated with the, if we put it with the inputs, because it's incorrect to say 0, 0, 0, 1. I mean, if we are in Mealy model, it will be much easier. You'll just copy it here. But in this model, it will be, let me double check here, 6, 7, 0, 0, 0, 1, 0, 0, 0, 1. So it will be 4 and 5, which is incorrect because it's with 6 and 7. So in this one, Z, you need to don't do it in this way. Do it in the conventional way, which is just the midterms. Z, it can be correct if you are using Moore model, then you can copy it from the inputs. But here, I think it will be a difference. Then you know how to do K-maps, so you can group these two and group these two. Here, group these two and group the other two to get the functions, and that's it. Any question? So I showed you the overall idea. I showed you that how to use the states, this state, or to use K-maps in and the state tables, how to put them at the same time. Now let's go to the design. That's our today's topic. So design, there are some procedures to do the design. The first part converts the written problem, what I recommend to make it as a flow chart. Then from flow chart, you can create state table and state diagram. So that's very important, which is the same when we discuss about the Cook machine example. We converted this to flow charts. Then we did the state table and state diagram. So that's the first part, which is to reach the state table and state diagram. So derive the state diagram, then verify the state table, make sure it's fine. Then there's something called use state reduction techniques to find the minimum state table. Most likely, I don't think we will have time to go to state reduction, but let's forget about step 3. We will talk about this later in case if we have time, if we have enough time. So then assign the states, which is after assigning, make, for example, state A, B, C, D, and so on, and make your own state table, state diagram. You can assign, like, for example, state A, as I showed you here, make it 0, 0, B, 0, 1, like converting this state table to this one. That's the overall idea. Then after converting state table to this parts, you can do it in K-maps like this way, find the functions. That's the part which is generates the state transition. Then find or also make sure that's which flip-flop that you need to use. Are you going to use T flip-flop, JK flip-flop, D flip-flop? Of course, D flip-flop is the easiest between them. Then produce a logic equation from K-maps and make sure that the logic equation is consistent with the flip-flop that you have. Then draw the logic circuits. So it's very important after finding all of this to draw the logic circuits. Okay, let's look at this example. Design a D flip-flop. Let's assume we already have a design problem. After that, we convert this problem into a logic state table. So that state table looks like this way. How can we make our design? So let's make the state diagram. So state diagram, we have 4 states, A, B, C, D. Is this in Mealy model or Moore model? This is in Moore model. Mealy model actually, because Moore model will include the inputs at the states. So let's follow him. If the input x is 0, we will remain at A. The output is 0. If the input is 1, we will go to B and the output is 0. While with B, if the input is 0, we will go to A and the output is 0. If the input is 1, we will go to C and the output is 1, while with C, if the input is 0, it will go to B, and the output is 0. If the input is 1, it will go to D, and the output is 0. Now with D, if the input is 0, it will go to C, the output is 1. If it is 1, it will remain at D actually, and the output is, if it is 1, and the output is 0. That's how the state diagram do. Then, following the steps, we need step number 2, assign binary values for the states. Now, how many states do we have? 1, 2, 3, 4. 4 states. Remember, flip-flops or number of states, or actually number of flip-flops, or no, number of states. Number of states equal 2 power number of flip-flops. So, number of flip-flops equals to log base 2 number of states. Or actually, you don't need to say log. You can just use the other first one to get this one. So we have 4 equal 2 power x, which is number of flip-flop. 4. So which is 2 power 2 equal 2 power x, therefore x equal 2. Then we can say number of flip-flops equal 2. Okay? And that's what we can say, like when we assign a values, we can say 2. Do you agree with me? Okay? Now, we can say that state A is actually 0, 0, B 0, 1, C 1, 0, D 1, 1. Then, what I encourage you is to redraw the states table. So here is states, but put the new values. 0, 1, here is input x. Input x, and I'm going to make the states as, I can call it as y1, y2. So here is y1, here is y2. Then A, 0, 0. Then B, 0, 1, C, 1, 0, D, 1, 1. So here with states A, it will go to A with 0, 0. So it will be 0, 0 over 0. With 1, when it's 1, it will go to B, which is 0, 1 over 0. So I'm just trying to drop this one here. Substitute the values. Then B, A, which is 0, 0 over 0. C, 1, 0 over 1. D, here at C, let's go to C here again. Third row, we have B, which is 0, 1 over 0. And let me make it over. Fix this, it's over. It's not 1. Then it will go to D, which is 1, 1 over 0. Now here C, which is 1, 0 over 1. Here is D, which is 1, 1 over 0. Okay? That's the state table after I assign the values. Okay? Now, the good parts, if we use the K-maps, the modified version of the K-maps, which is like this, we can assign the values easy. So here is y1 star, here is y2 star, here is outputs. And the outputs, what's the outputs called here? I'm going to assume the output Z. Z, which is the outputs. Now, how can we find the values? Y1, we know the location of the inputs, or at any here, y1, y2 over z. That's how it will be. So y1 will be this. So we're going to draw it. I'm going to write them like this way. Here is 0, 0, 0, 1. 0, 1, 1, 1. That's for y1. y2 is the others, 0, 0, 0, 1, 0. So we have 0, 0, 1, 0. Here 1, 0, 1, 1. 1, 0, 1, 1. Okay? Then for the outputs, here 0, 0, 0, 1, 0, 1, 0, 0. So we have 0, 0, 0, 1, 0, 1, 0, 0. So making this in K-maps will be much easier into this format. Okay? Then we can create the equations for each one, do the K-maps for each one. So actually, we can group these two here and these two here. We can group these two here and these two like this way. While for the outputs, this will be isolated. Right? Is this clear? Now, remember, here is x, here is y1, here is y2. Then the same, here is x, here is y1 area, here is y2. Here is x, here is y1 area, here is y2. So, for y1 star, it is located at, here is y2, while for x, yes, it will be with y2, x. Okay. Plus, that's for the first one. The second one, which is, it's not x, which will be with y1, while for y2, this is the area of y2, y1, y2 bar. Because here is the area of y1, then y2 bar. Okay. Let's look at the other one. y2 star will be, now this is the area of y1, y2, then plus, this is the area of y2 bar, x. Okay. y1, y2 bar. Yes, I think it does make sense. Okay. Then here for z, it will be locate these ones. This is we cannot group it, therefore it will be three variables. It will be x, or let's look about y1 bar, y2 x plus y1 y2 bar x bar. Just kernel maps. Okay? Does this make sense? So we have now the equations of all those three. How about if someone say, if I didn't make the table like this way, if I make the table based on the generalized table, how can I get it? The answer? If you make the generalized table, yes, you can. Here's step number, this is step number 3. Or, step number 3, we can say generalized table, which is basically, here is the present states, which is y1, y2, inputs, x. We have a new state here, which is y1 star, y2 star, and here is outputs, z. Then just translate that table into here by assigning the values. Here is 0, 0, 0, 0, 0, 1, 1, 0. I'm sorry, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. So after translating this here, it will be 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1. And the outputs will be like 0, 0, 0, 1, 0, 0, 1, 0. So by looking at the midterms, this is equivalent to M0, M1, M2, M3, M4, M5, M6, M7. Then we can say by looking at Y1 star, it will be the sum of midterms of, we have one here which is 3, 5, 6, 7. 3, 5, 6, 7. Then Y2 star will be the sum of midterms of 1, 4, 5, 7. 1, 4, 5, 7. And Z will be the sum of midterms of 3 and 6. Then you can translate this into here. Put them here. So it can be this step number 4. So whatever, if you use the generalized table, just locate where are the location of midterms, then you can put them in K-maps. If you are using the table like Mealy model, you can use put in the values even without the need to find the midterms. Okay? Then you can calculate the equations. Let's see, 0, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay. Yes. So after that, after finding all of the equations, which is now, let's go to step number 5. Again, we just calculate the equations as y1 star equals to y2x, y1, y1 bar. y2x plus y1, y2 bar. And we just calculated y2 star as y1, y2 plus y2 bar x. y1, y2 plus y2 bar x. And z, y1 bar, y2x, y1, y2 bar x, y1 bar, y2x, plus y1, y2 bar, x bar, plus y1, y2 bar, x bar. Okay? So here's a summarize of the equations. After getting the equations, now we need to translate this into electrical circuits, or into the digital logic circuits. How can we achieve this as a digital logic? Most likely, this is y star, this means y1 of t plus 1, y2 of t plus 1. So these two, time dependence. Therefore, we need the storage elements, which is we need the flip-flop. So this y1 star, y2 star, we need flip-flops. One flip-flop for this one flip-flop for this one. While for Z, we don't need a flip-flop because it's not related to the time. This is outputs, no need for flip-flop because it's independent of time. Okay, how can we achieve this? Let's assume we need to use a D flip-flop. D flip-flop. What's the table equation of the D flip-flop? Q star equal D, right? Or Q of T plus 1 equal D. That's the D flip-flop. Now let's assume a D flip-flop been used, then we can say that, here I'm going to call it like A. D flip-flop, so it's going to be Y1 star will be equal to D, which is Y2X plus Y1, Y2 bar. Okay? Then I'm going to call it as D1. For the other flip-flop, D2, Y2 star equal to D2, which is Y1, Y2 plus Y2 bar X. Then Z will be Y1 bar, Y2X plus Y1, Y2 bar, X bar. Now, we know that what's D for each one. Then that's it. We are ready to build our design. How to build our design? Oh, we don't have space. Okay, let me move this here. Okay. Now we have how many inputs? We have only one input, which is X. So we can draw it like, let me use this one. Here is X. And here is X bar if we need it. We have two flip-flops. Here is the first flip-flop, D. Here is D1. And here is the clock cycle. If you need to put the clear, that's fine. If you don't need, it's not necessarily. Here is the clock. Here is the other D flip-flop. Call it D2. Here is the clock. The output of D1 will be just called Y1. Here is Y1 bar. Here is Y2. Here is Y2 bar. Okay? Do you agree with me on this? Now let's look at the equation of D1. D1 is Y2 times X plus Y1, Y2. So we have two AND gates. Well, then there will be OR at the end. So there will be OR that is connected to two AND gates. So here is AND gates. Here is another AND gates. So the first one will be Y2. Okay, let me see if I can. Okay, no problem. The first one, Y2X. So here is Y2 and with X. Here is X. Okay? The second one, Y1, Y2 bar. So Y1, here is Y1. Y2 bar, here is Y2 bar. Okay? Then, let's go to D2. D2 is Y1, Y2. Or there's actually OR, then there's AND. So the first AND, and here is the second AND. Y1, Y2. So Y1 is actually, where is it? Here is Y1. We can take another branch of Y1 to go this way. Actually, I prefer to write it in a different way. Okay, I'm sorry. I would like to erase it so I can make it much easier. Okay, let me do it again. Because sometimes it looks like a messy. Okay, let me take each output and put it there. So here is Y1, Here is y1 bar. Here is y2, or let me start from the, okay. Okay, I need this to be nice way. Here should be location y1, y1 bar, y2, y2 bar. So let's start from y2 bar, y1 bar, y2. Then here y1 bar, then here y1. So here is all of the signals. Again, this is x bar, y1 bar, y2 bar. This will be nicer way. The clocks are connected together, so here are the clock cycle. Then we can make, since there is OR gates, then it's associated with two ANDs. Then the same way here, there is OR gates associated with two AND. Don't have enough space. Okay, D1 connected to Y2, which is this one, and X. Then the first one. The second one, Y1 bar. Here is Y1, here is Y2 bar. Then this one, Y1, Y2. Here is Y1, here is Y2. Then this one, Y2 bar X. Here is Y2 bar, and here is X. Now it will be much easier. Now the last one, which is Z, here is the output Z. I'm gonna make it here. There should be OR first, then there are two ANDs. So the first AND connected to Y1 bar, here is Y1 bar, Y2, X. Then the second one, connected to Y1, Y2 bar, X bar. And I'm going to erase the clock. Put it here, clock. And if you need to have a reset or clear, we can have it like this way. In case if you need the clear. It's active low. So here the clear, and there is top here, and don't forget there's a bubble at the clear. So that's design, can do the job. In case if we need to make it more realistic by converting this to NAND implementation or no implementation, you know how to do this. If you make it as NAND implementation, put a bubble here, bubble here, bubble here, bubble here, then they are all in NAND, and that's fine. And this is a NAND implementation. Then you can go to the lab, build these circuits, then that's it. Problem done. Yes?
If you're doing NAND implementation, you do that just to the output or to all of them? Or all the small?
Yes, to all of them actually.
Okay.
Of course, to everything. So now it will be more practical because in real life there is an AND gates. Then you can build it and do your own design. That's why it's called digital logic circuits. We are making hardware programming. So that program is based on elements. Like this is storage elements, this is and OR gates, etc. While again nowadays, most likely this is kind of old science. We are not using this in programming. We used to use an or high level languages, high intelligence level languages like C language, Python, C#, etc. There are a lot of languages there nowadays. So this was kind of old science, but it's very essential because that was in the past, before the inventing of the programming. That was how we used to deal with the problems. And there is other type of programming. There's assembly language, which is based on low intelligence languages, which is assembly, which will be a next topic in different course, in other course, which is called microprocessor. Then there will be how to deal or how to make the programming. Basically, you need to use the registers, and we're all familiar with what the register means. Then you can build your own program, software program by these registers. Then you need to store this into a microcontrollers or into a small computer. So the microcontroller are basically works as a small computer or a smaller brain. Then it can control the system to do the specific thing. So what your target as a programmer is what to store inside this brain or inside this microcontroller. Then here in digital logic circuits, this is our controller. We didn't need to use any parts or of controllers because this is the circuits. That's my design. That's how we do it. While again, simply, if you are doing this using C language or even like the Arduino, you can do it in very smooth way, in very easy way, and shouldn't take 2 minutes, or even you can find a code in the internet, open source in the internet, and you can do the whole job. But again, in this course, we are focusing on to the basics, how we used to do it in the past, how, if we need to make a microcontroller, how we can achieve this. So you can have a better understanding about this, then you will be ready for the next topic, which is how to make a small programs into the microprocessor. Even though when you will learn the microprocessor and you will learn the assembly language, you will not use it in your job. You will less likely use it in your job. Your job will be later after learning the high intelligence languages, which is, as I mentioned earlier, Python or C, etc. So you will see most likely all of these technologies, we will not use them. Yes. But actually it depends maybe in your position later. Maybe if you will go as a software developer, maybe you will use an assembly, because assembly language is consuming, when you program in the assembly language, it will have a low memory other than the C language. C language will consume a lot of memory. So there will be some limitations. That's why, therefore, when, for example, developing a software or even developing operating system, most likely it will be programmed on assembly, because it will consume faster, will make, even if it's very complicated, you can spend years on it, but it will be, it will produce the outputs fast system. That's why we see like the operating systems are growing, but sometimes it takes some time to grow because the development takes a lot of time. Okay, another example, this is the same example, but how about if JK flip-flop is considered, not D flip-flop? What do we need to do? Repeats the same steps from 1 to 5. So the final result, we got the output. What was the output equations? Y1 star, Y2 star, and Z. Y1 star, it was Y2x plus Y1, Y2. Y2x plus Y1, Y2 bar. Is that right? Yes. And the Y2 star, Y1, Y2 plus Y2 bar x. Then Y1 bar, Y2x plus Y1, Y2 bar, X bar. Y1, Y2 bar, X bar. So we already know how to deal with this. When we discuss D flip-flop, we used to say this is D, this is D. Then that's fine. That was in the past. Now we need to use JK flip-flop, not D. Remember, Z, there is no flip-flop, so Z will remain as is. No change on Z because there is no flip-flop. What we are worrying about, which is about Y1 star, Y2 star. How can we achieve this? Let's recall in JK flip-flop, the equations Q star equals to J Q bar plus K bar Q, right? Then we can say that Y1 star equals to Y2X plus Y1, Y2 star, Y2 bar. Then we need to convert this to be J1, Y1 bar plus K1 bar times Y1. Now the question is how to convert this to this. Look at the terms, which is Y1. Here we have Y1. Then we can say Y2 bar is equal to K bar, right? Is that right? We can compare it. Now, can we compare Y2 and X? We don't have Y1, right? So we cannot compare it. Is there any idea how to deal with this? So we already done with this term. How can we convert this term? Do you have a clue how to deal with this? We need to convert this one into this formats. So each term must include either Y, Y1 or Y1 bar. The first term, each term must include Y1 or Y1 bar. Here is Y1 bar, here is Y1. So here in the second term, there Y1 is already being included. Then this term, we can figure it out. But this term includes Y2, but there is no Y1. How can we solve this problem?
Y bar plus what?
Yes, great, that's it. Basically, there is a missing variable, and according to the algebra, the missing variable, for example, is Y1, so it will be Y1 plus Y1 bar equal to 1. So basically, we can say this one multiplied by 1 then we can say it is Y1 plus Y1 bar Y1 plus Y1 bar times Y2X plus Y1 Y2 bar. Then do your simplification. It will be Y1 Y2X plus Y1 bar Y2X plus Y1 Y2 bar. Now I need you to group Y1 alone and Y1 bar alone, each terms with this. So it will be Y1 alone, then plus Y1 bar alone. So let's put the terms. So where is Y1 here? We have Y2X, so here's Y2X. Here is this term associated with Y1, so we have Y2X. Here, this is Y1, so we have Y2 bar. So plus Y2 bar. Okay, let me erase it to make it better. Y2X plus Y2 bar. Okay? Does this make sense? Now, we can write it in the general formula because I need to convert this to be J1 Y1 bar plus K1 bar Y1. Then it's going to be like this. It's going to be like Y2X plus Y2 bar plus Y2X, or forget times Y1 times Y1 bar, which is equivalent to J1 Y1 plus K1 bar Y1. Okay, clear? Now I think you figured out. We know what's J, we know what's K. We can say that this is J1, this is K1 bar. So J1 equals to y2x plus y2 bar, K1 bar equal to y2x. Therefore, we need to convert this to K1, not K1 bar. So K1 will be y2 bar, y2x, all bars. Using De Morgan's, it will be y2 bar plus x bar. Okay? Is this clear? Now, how about y2? The second equation, y2 star equals to y1 y2 plus y2 bar x. Now, we need to convert this into j2 y2 bar plus k2 bar y2. Is this written into the general formula? Yes, actually. We can say this is equivalent to j2, actually equivalent to k2 bar. This is equivalent to j2, right? Or in other words, I can rewrite it as I think I messed up with something. Oh, yeah. Let's go back there. I apologize. Let's go back to this equation, then I will back to y2. Here, I messed up because j1 associated with y2 bar. So therefore, I'm going to erase this and erase this. Here is, I'm going to write it in the other formula because y2, j associated with y2 bar, with y1 bar. So it's going to be as, I apologize about this. So it will be y2x times y1 bar plus y2x plus y2 bar times y1. Now we can say this is j1, this is k1 bar. So as a result, j1 will be y2x, while k1 bar will be y2x plus y2 bar. Therefore, k1 will be y2x plus y2 bar, all bars. So I missed between y1 and y2. Then, let's go back to the second equation. We already have y2 bar, that's fine. So we can write it in the general formula such that x times y2 bar plus y1 times y2, this is equal to j2 y2 bar plus k2 bar times y2. So by making this comparison, we can say that this is j1, this is, I'm sorry, j2, this is k2. So j2 will equal to x, k2 will equal to k2 bar will equal to y1. Therefore, k2 will equal to y1 bar. Okay? So as a result, let me write a summary. In summary, y1 star equals to j1 times y1 bar plus k1 times y1, k1 bar times y1, such that j1 equals to y2x, k1 after putting the bar because we remove the bar, y2x plus y2 bar. Then this is the first equation. The second equation, y2 star equals to j2 y2 bar plus k2 bar y2, such that j2 equals to x k2. Let me write k2. K2 equals to Y1 bar after putting the bar. Then the last one, which is Z, which is the same, no change, it was Y1 bar, Y2x, Y1 bar, Y2x, plus Y1, Y2 bar, X bar, plus Y1, Y2 bar, X bar. Then we are ready to draw the digital logic circuits. So step number 6, draw the logic circuits. DLC, which is the name of this course. Digital logic circuits. So we have 2 JK flip-flops. Here is J, here is clock, here is K, let me call it J1, K1, here is the clear, here is Y1, here is Y1 bar, then let me draw the other JK flip-flop. Here is J2. We will assume it's synchronous every time. Our design is based on the synchronous. So they are all sharing the same clock, K2. Here is the clear. Then here is Y2 bar. Then we have one input, which is X. So I'm going to make the input X goes this way. Here is X bar. Goes like this. Then here is Y1 bar, Y2 bar. So it will be like this. Here is Y2 bar, go here. Here is Y1 bar. I'm sorry, Y1. Already done with Y1 bar. Now Y2 bar, then Y1 bar, then this is Y1, so the sequence, this is X bar, Y1 bar, Y2 bar, then it will be much easier to follow. Then we need to say what's the equation of each one in J and K. So for J1, here is J1, Y2X. So there is AND gates between Y2 and X. So the first one will be connected with Y2. Then the second part will be with X. Y2, here is X. Now for K1, there should be inverter. Then there will be OR gates. Then this OR will be between Y2 bar, here is Y2 bar, and there's Y2X. So I'm gonna put AND gates here, here is Y2 bar. Then we need to put Y2, here is X. Okay, does this make sense? Let's go to J2. J2 equals to X, so easy. Equal to X. Don't forget to put like bubble or to mark down where is the connection. K2 is connected to Y1 bar, which is this one. Then what's left? Connect the clocks. This is the clock. Then what else? Just the clear. Keep in mind there's a bubble at the clear because it's active low. That's our standard to make the clear active low. Clear and power. Okay, that's the JK. We are not done yet. Don't forget the output Z. How can we connect the output? Look at the equation, which is Y1, Y2, X, Y1, Y2 bar, X bar. So basically for the output there should be OR, then there's two ANDs. This is the same way as we did in the previous example because there's no change on the outputs. So it will be Y1 bar, Y2X. Here is Y1 bar, here is Y2, and here is X. Y1 bar, Y2X. Then the other term, which is Y1, Y2 bar, X bar. So Y1, Y2 bar, then the other part X bar, the last one. Here is X bar. And recall again, this is X, X bar, Y1, Y1 bar, Y2, Y2 bar. Then my design now is complete, and that's it. This is a complete design model using JK flip-flop. Any question about this? So the whole idea now we are making a complete after converting the return problem into the logic circuit or into the state diagram or into the state table. And we already know how to convert any problem into the state table and state diagram, right? We already done this with Mealy model, Moore model, and you already seen this in the second exam as well. So you should be aware how to make and convert any problem into state table or state logic. Okay, there is example number 3. Converts, or you have use a D flip-flop design circuits to make this following behavior. So the first thing that you need to keep in mind, using D flip-flop is much easier than using the others because you assume Y equal to D. If you are using JK flip-flop, it will take some time. T flip-flop, not every problem. I cannot apply T flip-flop for every problem. There's a special cases that can be done for T flip-flop. Because actually you can say that the T flip-flop and JK flip-flop, T flip-flop is a special case when J equal to K. If J equal to K, then we can apply T flip-flop. Otherwise we cannot. Therefore, not every problem, I cannot apply T flip-flop for every problem, or it will be too complicated. Therefore, in case if you see design using T flip-flop, you can apply it in the same way that what we did into JK flip-flop. But if you figure out J and K are equal to each other, then that's T flip-flop. Okay? So you are still required to apply T flip-flop, but again, not every problem. We cannot apply to any problem. But if you see it in the exam or in the quizzes, apply T flip-flop, then basically it is applicable. So you will not say you cannot apply it. There should be some way to do it. And also I think there will be a quiz on Friday. The quiz will be in design problem. Like you will have a problem and make the design, which is very similar to what we discussed here. Okay, using a D flip-flop design circuits to get the following behavior. We have state A, B, C, D, and there's something called unknown states. There's something in U. Unknown state. This means we have missing information. How can I deal with this missing information? Which is we apply don't care. Any missing information, just make it as don't care. Okay? How many states we have? 4. 4 states, or in other words, 2 power 2 states, which is equal to our number of flip-flops. Therefore, we have 2 flip-flops, or 2 bits. And these 2 bits, we can assign them like Y1, Y2, 0, 0, 0, 1, 1, 0, 1, 1. And you are free in your design. If someone say, let me choose A as 1, 1, you are free, that can be fine. Let me choose C as 1, 1 and D as 1, 0, like gray code, that's fine. Whatever more convenient for you, that's fine. But I encourage you to be consistent, like the same as we used to do in class, like A00, B01, and so on. So it will be easier in grading. But otherwise, whatever you do, that's your own design, and you are free. So this is A, this is B, this is C, this is D. So we can make the state tables in either merely model, or we can do it into the generalized table. So let's do it in merely model first. Merely model. So we have here present states. Y1, Y2. Here is input X when it is 0, when it is 1. So for the present states, we have 0, 0. 0, 0, when the input is 0, it will remain at state A 0, 0, and the output is 0. If it is 1, it will go to state B, which is 0, 1, and the output is 0. Now with state B, 0, 1. If it is 0, there is no information. So don't care, don't care. And the outputs don't care, because there is some missing information. So any missing information, again, we make it don't care. Look at state B. If it is 0, no information. If it is 1, it will go to C. So if it is 0, don't care. That's why I put D, D. And the output, there is no information, so we put D. If it is 1, it will go to C, which is 1, 0, and the output is 0. Now look at state C. 1, 0. State C, if it is 0, no information, therefore don't care, right? Don't care over don't care. If it is 1, look at C. If it is 1, it will go to D. If it is 1, it will go to D, which is 1, 1, and the output is 0. Then the last state, which is D. If it is 0, don't care. We don't have information. Don't care, or don't care. If it is 1, the output will be 1, but it will go to unknown states. So it will be don't care, but over 1. Why over 1? Because the output will be 1. That's if the input is 1, the output will be 1. That's written here. Okay? So do you know how did we construct this? That's based on the Mealy model. How about the generalized model? The generalized model, we can do it like this. Here is present state. In the quiz or the exam, you need to do one. Don't do it both. Don't say generalized table or don't write both or Mealy model. It's up to you. I'm just showing you these two, then you can do whatever more convenience. So here is present states. Which is Y1, Y2. Then here we have inputs, which is X. And then I send two parallel lines. We have next states, which is Y1 star, Y2 star. Then we have outputs, which is Z. Let's make it as a truth table. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Now what will happen in the next states? Again, follow with this. If we are A and the input is 0, we will remain at A and the input is 0. If we are at A, input is 1, we will go to B and the output is 0. If B input is 0, we don't know, so don't care. If the input is 1, we will go to C and the output is 0. Now with C, if the input is 0, don't care because we don't know it. If the input is 1, it will go to D which is 1, 1, and the output is 0. Now with D, if the input is 0, don't care, we don't know it. If the input is 1, which will be, output will be 1, but the others are don't cares. Okay? Then we can say here is M0, M1, M2, M3, M4, M5, M6, M7. Then after that, we are ready for the next step, which is doing kernel maps. Okay? So this is one way. If generalized model, we already have the midterms, or you can use the Mealy model and do the kernel maps easy without looking at the midterms, actually. We can do it in an easy way. So basically, locate these and substitute them there. So let's work at y1. Here is y1, here is y2, and here is z. So for y1, the first column, 0, D, D, 3 Ds. 0, D, D, D. The second column, 0, 1, 1, 0, 2 ones and D. 0, 1, 1, D. Let's go to y2. In y2, 0, D, D, D. So 0, D, D, D. Second column, 1, 0, 1, D. 1, 0, 1, D. Okay? Now for the outputs, 0, D, 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 or 3 zeros, 1. 0, D, D, 0, D, D, D. Then 0, 0, 0, 1. 0, 0, 0, 1. I'm not sure about the output because here M2, M4, 6, 7. Okay, so okay, let's keep this design. Then, in the output, now we need to group each 4 or each 8. Can we group 8 in Y1? No. Can we group 4? We have 2 1s and 2 Ds, so we can group them like this way. Group this. So we can say Y1 is actually, by grouping this 4, recall this is the area of X, this is the area of Y1, this is the area of Y2. So Y1 will equal to Y2, Y1 star. All of them are stars. Okay? Then here, how can we group it? We can group these 4. And for that one, we cannot group 4, we can group 2. So this is the area of Y1, this is the area of X, this is the area of Y2. So Y2 star, the biggest square, the 4, which is going to be Y1, plus, what's the other, which is, we have X and Y2 bar. So Y2 bar X. Then let's look at Z. We can group only these 2. Here is Y1, here is Y2, and here is X. So it's going to be with Z equals to Y1, Y2 bar. Okay? After making this, as a result, I can write them here. Like Y1 star equal to Y2, and we need to use a D flip-flop, so here is D1. Y2 star equals Y1 plus Y2 bar X, this is D2. And Z, remember, Z there is no flip-flop on it because it's time independence. Then now we know what's D1, we know what's D2. And this is Y star. Then let me finish just drawing the digital logic circuits. I'm going to take a few minutes left. In case if you need to leave, you can leave. I don't want to affect this in your, if you have other arrangements. So Here is D flip-flop. Here is the other D flip-flop. This is D1. This is the clock. D2. Here is the clock. This is Y1. Y1 bar. Here is Y2. Y2 bar. Here is the clear. Then D1, and let me write here is input X. So D1 equals to Y2. Then actually you don't need to make it too complicated, so you just say D1 equals to Y2. So here's Y2, we'll go to D1. Then for D2, it's actually Y1, there's OR gates. Y1, then there is Y2 bar, Y1 here, and there is AND gates between Y2 bar and X. So here is Y2 bar and X. Okay. Then the clock can be connected. Let's make it like this. Here is the clock, and the clear can be connected like this. Clear and active low, and even X actually we can make it like this way. So if you want to do it in the other way, that's fine. Then the last thing, which is Z, there is AND gates, AND, yes, which is connecting Y1 and with Y2 bar. And that's Z. Then that's the design that we can do. Okay, any question? Okay, so that's it for today. Don't forget to study for the quiz